So Luke is a PhD student based at London School of Hygiene and Tropical Medicine, and he's going to tell us more about his PhD project. So go for it, Luke.
Hi. Thank you very much for having me. So as Ed just pointed out, I'm coming up towards the end of the first year of my PhD. First off, thank you very much to the modelling teams at LSHTM, there's some economists and behavioural scientists at Imperial, and then Katie Turner, who we've met this week. The project is largely COVID-based. It's about understanding, we've got all this data that's collected during pandemics, so how can this shape outbreaks? How can we utilise this? So a quick bit about how I got here today and sort of what I've done, which is quicker than saying what I've not done. I did my undergrad in maths. This ended with a thesis on sort of branching process models. So if an infected individual enters a population, what's the probability of an outbreak happening? And we sort of extend this to age and structure-based age and settings to sort of look at the effect of school closures or workplace closures. As I finished that, an internship came up at the Big Data Institute about modelling the impact of vaccines for trachoma elimination. This was an individual-based model, which, because every individual had their age, number of times they've been infected, viral load, it's sort of the number of combinations that isn't very healthy for a compartmental model. And then I came along to do a health data science master's. The thesis there was sort of predicting immune responses to influenza vaccination based on some demographic factors and your pre-existing immunity against historical strains. It's quite difficult to do, especially when you've got your covariates and your outcome variables both have measurement errors. And now I'm starting a PhD. So throughout this, we'll use COVID in England as a case study where you've got this intersection of lots of different data streams. So, as I'm sure most of us know, respiratory transmission is shaped by quite a few different things. You've got the susceptibility of hosts, you've got properties of the pathogens, you've got contact intensity, which is further mediated by, social distancing, mask wearing, things like this. And of this, there's already some kind of fixed structure within the population. So we know that there's some structure between how different age groups interact, where they interact. There's obviously existing inequalities based on essential workers whose behaviour is constrained, as well as higher deprivation regions who maybe have higher contact counts during epidemics. But then there's a huge variable component to behaviour. As we know, a lot of people change their behaviour even before mandates were put into place. So maybe people stayed at home a bit more before stay-at-home orders were officially put into place. So it's sort of important to have models that recognise how this behaviour is changing throughout pandemics. One thing I'll come back to a few times in case no one's seen this, the comics data ran for 2 years throughout COVID and asked people to report the number of social contacts they have each day, including the age and setting. It sort of gives you an idea of how age-based contacts change throughout the pandemic, and sort of very useful for understanding both policy impact and the impact on transmission. There's a lot of data streams, so I think one question is how can we use these and how can we combine them? So just to elaborate a little bit more on what these streams are, like I say, the comics, this was sort of age-structured weekly contact counts. They were sort of self-reported. Mobility, this is like a mobile phone proxy, so measures where people spend their time, how much relative time people are spending in, parks, grocery, retail, different settings. And then there's other attitudes, so like risk perceptions of how much trust people have in the government, how much people feel they have the capacity to change their behaviour if they want to. And immediately from the behaviour change frameworks yesterday, you can see how these start to slot in. So a few data streams I'll show you. The first one is a kind of transformed scalar summary of a contact matrix. But like I say, the mobility, the second graph shows you that people are spending less time in retail-based settings, and there's a lot of fluctuations here. The bottom two show from the YouGov attitudinal survey throughout COVID, so how likely people are to self-isolate and how afraid people are of the pandemic. So I've shown population-level averages on the bottom here, but of course, within that, the population is made up of a lot of individuals with very heterogeneous attitudes. That's a lot of streams. They differ. They differ in terms of populations in each data set, cadence, coverage, cost, likes, coarseness, how accurately they capture behaviour that's relevant to transmission. So the main question I'm looking at to begin with is, if we have multiple of these data sets at our disposal, sort of how can we systematically combine them to estimate transmission rates and forecast transmission? just to overcome models which rely on single sources as their input for data. How I'm approaching this, and I'm well aware that there's probably other methods to do this, firstly using a renewal process where infections today depend on infections in the past, sort of weighted by timings between infections and reproduction numbers, and use a sort of Poisson distribution to capture some noise. What we can do from that first line is take expectations of each side and take logarithms, and it turns this into a regression formula, which then lets you depend RT on other behavioural covariates. So if I want to see how well a certain behavioural stream predicts changes in transmission, I can sort of look at the coefficient between those and the uncertainty in that coefficient. Incidence data of choice. England was quite fortunate in the sense that we had the ONS COVID infection prevalence survey. So it estimated each week what proportion of the population had COVID. Some great team at LSHTM made a package to sort of deconvolve that to estimate daily infections, which creates a sort of relatively unbiased source of surveillance data compared to like reporting and hospitalizations, which might be biased. And I'll quickly show you some of the forecasting comparisons that I'm going to do and score forecast performance. So like I say, I've got a few models. Start with the baseline, which has no behavioural covariates. Introduce a model with Google Mobility, one with contacts, and then one with sort of combined, and see how mixing and matching different streams affects performance. As an illustration only, which is why I've stripped off numbers from this plot, I've got the black line, which is like true infections, and then I've got the other coloured lines, which are sort of forecasts with these different models, which use different data streams. And I'll be sort of looking at how well do these capture true forecasted values, like how sharp are these confidence intervals, and is the times where using different data streams causes you to overall underestimate transmission. Now, another issue, if we've got these different data streams, they're not all available exactly as and when you want them. There's obviously reporting delays. So if you run a social contact survey, it takes time to fill out the survey, process it, report it, make it public. So what I'm sort of interested after that is how would this look in real time? It sort of avoids this nice optimistic setting that I've just described where you have all the data that you need. So I think maybe the bottom graph kind of illustrates that different data sets arrive with different reporting lags. And we'll think a bit about how much does sort of performance degrade in this setting. Secondly, building on sort of frameworks that were mentioned yesterday, this observed behaviour doesn't explain why people change, and I think that's relevant to policy if you want to help anticipate determinants of change throughout pandemics. And for example, if you try to make the population more scared, for which subgroups will this actually have an impact, and what impact will that be? And it sort of helps separate a little bit between structural constraints and attitudinal motivation, or attitude. Yeah, I'll leave that. There's a few different frameworks that are available that look at different components, whether it's self-efficacy or whether it's perceived severity, things like this. And one thing we're thinking about is different sort of attitudinal variables are available in different data sets, which makes it quite difficult to get an idea of the overall sort of attitudinal makeup of the population. But if we just use one, Comic's survey collected attitudinal information alongside the contact behaviour. So this includes perceived severity, risk of infection, how likely you think you are to be able to reduce your contact behaviour. We'll run a latent class analysis to see whether sort of natural behavioural archetypes or groups emerge within this population, and then see whether those sort of meaningfully translate into predicted contact counts. Of course, a lot of these relationships, the relationship between attitudes and observed behaviour will be mediated by physical constraints. And it might be of interest, for example, to look at not just the mean predicted contacts, but also variability. So if fear is high, for example, would you see a greater variance and dispersion in observed contacts? And that could, in theory, give you an idea of how poorly calibrated some transmission models might be, because you've not captured this heterogeneity within the model. Again, I'll realise I've only got 2 minutes left. So like I say, you've got this sort of mixes of like compositions of archetypes within the population, and if you just look at mean observed behaviour, it sort of masks a lot of these changes. It sort of overlooks how shifts in these different groups can move transmission, and in practice, a lot of the signal, from the epidemics can change these attitudes in some groups within the population. So I think what we're going to look at is what here I think is kind of a mean field approximation. If I know what these different groups are, can I look at how they evolved throughout the pandemic and what this means for transmission? So maybe I have different behavioural archetypes, and the sort of prevalence of each one shifts throughout the pandemic, which plausibly shift transmission. Potentially, if you know how the composition of people are shifting, maybe you can anticipate there's going to be a downturn, there's going to be like a peak during transmission, which you might not capture if you just look at average behaviour. Yes, we've thought about a latent transition analysis, and I'll spend a few years thinking about that. A future potential avenue, which I'll touch on quite lightly, is that Imperial have some data sets on encoded communication data. So I think this is really a few steps upstream from the observed contact behaviour that I've just described. But that's the sort of lever that policymakers have. You're communicating things, people are being exposed to different media and information, which plausibly affects your attitudes and your behaviour and so on. So we've got time series of basically all the information that came out of people's mouths during COVID, encoded by urgency, clarity, which aspects it's stressing. This was high frequency, is available in almost real time, unlike those 2-week reporting delays with some of the social contact data. So in theory, if we have this information available to us in real time, can we get a better understanding of behaviour that's happening now and how this in turn affects transmission? I'll stress I'm not an expert in causal inference, so I think a lot of this will be predictive, and there's other people at Imperial that are running factorial studies to help establish causal relationships. That's time, but I think I'll leave a few, just the sort of 3 aims and potential future avenue for the PhD, and I think quite related to the sort of data needs component of this workshop. There's lots of data sets, and I think there's a risk of ecological association. Maybe I'm comparing different data sets from different populations, and it's hard to establish individual level conclusions. So how do you mix and match these data sets with different information is something that we'll think about. Thank you.